Good morning, everyone. My name is Xinyi, and today I'm excited to present our research, sharing frictions among online video viewers, exploring the design of effective communication for aesthetic chills. This work was conducted in collaboration with my schoolmates, Zeyu Huang, Yuanhao Zhang, and under the supervision of Professor Xiaojuan. As we all know, online video platforms such as YouTube have become increasingly popular, offering a wide variety of content that often triggers emotional responses in viewers. One such emotional response is frisson, also known as aesthetic chills or thrills. Frisson is a psycho-physiological phenomenon that occurs when people experience intense pleasure, awe, or surprise while watching emotionally arousing content, like music performances or movies. However, current online video platforms lack effective ways for viewers to share their frisson experience with the others in real time. Although they contain abundant arousing videos like music performances and cinematic videos, the audience can only communicate their emotions and feelings in text-based manners like the comment area or the time-synced comment. The comment area cannot capture the passing moments of frisson in a timely manner, and both textual approaches demand extra cognitive load to write and read, to externalize and resonate with each other's feelings. Therefore, we would like to create a novel communication channel for video viewers to communicate their frisson moment. So sharing frissons, we automatically aim to create a sense of watching together for online video viewers and amplify the emotional contagion among the audience. To realize our goal, we propose an approach that unobtrusively detects the viewer's frissons using skin electrodermal activity (EDA) sensors and presents the aggregated data alongside online videos with synchronized timeline. We designed 3 different feedback mechanisms to encode viewers' frisson experience. The first is the ambient line design. It is an ambient line effect attached to the boundary of the video that glows at viewers' frisson moments. The second is the icon design. It is a size-changing lightning bolt icon positioned at the corner of the video screen that animates during a frisson moment. Finally, the vibration design is a linear vibration motor at user's fingertip that vibrates at frisson moment to provide haptic feedback. Our implementation consists of 2 main parts, a sensor module and a feedback module. The sensor module captures viewers' EDA data using a custom-built sensor pipeline, which includes a Groove GSR sensor and a Raspberry Pi 3B Plus and an analog 2-digit converter. The EDA data is then processed and stored in a local MongoDB time series collection. The feedback module is implemented as a browser extension that modifies the video page's content to display the frisson feedback. The extension synchronizes the feedback with the video playback progress, ensuring that the frisson data is presented in real time. Before conducting our study, we selected 4 sample videos that were likely to trigger frisson from 2 online video platforms. We also wanted to ensure that the videos can draw the majority viewers' attention and interest. And selecting multiple videos could reduce the bias of content and a platform preference. We require the videos of those selected categories should be generally arousing, and the video length should be between 2 and 7 minutes. To researchers that frequently visit online video platform, independently select 1 to 3 videos from each candidate categories, and they cross-validate each other's choice to decide the videos that triggers frissons the most. The final videos include 1 orchestra live performance, 1 pop music live performance, 1 superhero-heroine movie mashup, and 1 anime mashup. To collect frisson data from participants, we ran a data collection session where 20 participants were invited to watch the selected videos with the same device setup and wearing the EDA sensors. The orders of videos was adjusted using balanced allotting square. To extract frissons from the raw EDA sensor data, we apply the following steps to each EDA time series. A low-pass filter to eliminate the sensor's own noise and improve the signal-to-noise ratio. A moving average filter to tackle the baseline drift. A normalization to scale the data into 0 to 1. Peak detection and signal quantization to find out frisson moments and convert the time series to binary. After processing each EDA time series, we averaged all the series by video and ended up with one aggregated frisson data for each video. To evaluate our approach, we conducted a mixed method within a subject study with 48 participants. The study consists of watching 4 different video clips with each of the 3 feedbacks designed and a baseline condition without feedback. Participants completed questionnaires and participated in semi-structured interviews to provide insight into their experience. As a quick view of our research, our frisson sharing approach can effectively ease the sender's cognitive load of initiating effective communication while watching online videos, delivering other viewers' frisson experience to the receiver in a lightweight and straightforward way. When comparing the usability among the 3 designs, 2/3 of the participants found it harder to use the icon design because it is at the corner. However, the rest argued that it is silent enough. Vibration feedback was favored the most, with additional merit of its novel multimodality user experience. Nevertheless, some participants thought it was distracting. Furthermore, participants suggest a strong social attribute to this effective communication channel. It successfully created a sense of watching with the others, fostered emotional contagion among the audience, and intensified their emotional experience while watching the online videos. However, the strong social attribute also led to diverse attitude towards this communication channel. As it became a way of self-disclosure, some participants worried that the consequences of contribution their data to the aggregated pool. Some participants also suggested more control over when and with whom they shared their frissons, similar to how they would require autonomy in their social applications. From a higher level perspective, we highlight 3 major purposes of using these frisson sharing features, from participants' comments, to fill the data, seeking resonance and sense of watching together, to use the data, augmenting the video watching experience, and to analyze the data, overviewing the audience reactions. They led to different preferences and requirements of the feedback design and different possible negative experience while using this channel. More on this is elaborated in the full paper. In conclusion, our findings demonstrate the feasibility of using physiological reactions like frissons as emotional processes with the help of ever-developing sensing technologies. We also show the potential of using frisson sharing as an effective and engaging way to enhance the social experience of online video viewers. We optimistically anticipate a wider usage of sensor-detected frisson as an effective communication channel beyond the scenario of online videos, such as live streaming or virtual reality environments. From there, we also propose 3 future research directions. Future work can conduct in-depth signal data analysis to see whether users' physiological responses are also influenced, provided others' frisson data. It is also interesting to see whether users can identify the authenticity of the frisson data. Similarly, we may want to ask how to ensure the authenticity of the physiological sharing. Lastly, if the frisson sharing feature is deployed in real life, will it shift user habits on online video platforms? It may be a positive shift towards an active video commenting culture, or it can be a negative homogenization of high arousal videos. This is the end of our presentation. Thank you for your attention, and we hope you are also thrilled by our findings.